of the Earth. Consequently, the lunar module takes on handling characteristics which differ greatly from those of any previous vehicle.
400 feet down at 9. Stay forward. 10 and 50 feet down at 4.
The astronaut could scarcely wait until he was 300 feet above the lunar surface to get familiar with the handling characteristics of his vehicle during the landing phase.
300 feet down.
Clear for landing simulation.
He had to learn before he ever left the Earth.
His altitude is 300, airspeed about 27. 3 minutes to JP4, 50%. Thank you.
Airspeed approaching 40% roll.
Okay, crosswind. Descent rate's 10. Altitude's 200.
It was this requirement that brought about the development of the strange-looking flying machine called the Lunar Landing Training Vehicle.
Altitude's approaching 100.
1 minute to 50%.
Thank you. Descent rate's 4. Altitude's 100, descent rate's 4, airspeed's 5.
Touchdown.
To be worthy of its name, the Lunar Landing Training Vehicle, or LLTV, had to have virtually the same handling characteristics as the lunar module itself. When studies first began in the late 1950s and early 1960s, it was by no means certain that a pilot could even control such vehicles. They were so different that much of the basic engineering design data developed from the time of the Wright brothers' flight at Kitty Hawk in 1903 until the experimental aircraft flights of our own era simply did not apply. Even in the case of vertical takeoff and landing vehicles. A special lunar landing research vehicle was built, then flown 286 times during the mid-1960s to evaluate lunar module handling qualities during the landing phase. Procedures had been developed with fixed-base simulators and computers. While the research vehicle was also used as an interim trainer, the vehicle designed explicitly for training, the LLTV, became available for initial test flights in late 1968 and for lunar landing training several months later. Like the lunar module itself, the LLTV is totally different from any conventional aircraft in the way it handles.
The primary reason for flying the LLTV is to train pilots to maneuver in a less than 1G gravity field. While this is a novel task to the pilot, it is not very difficult, but I would like to make the analogy of learning to ride a bicycle. The first time you try it, it's very hard, but after a little exposure, it is quite manageable. To relate this to layman's terms, we'll use a conventional helicopter that the pilot is used to flying in a 1G gravity field. Here, to get significant acceleration and deceleration rates, only small degrees of pitch attitude changes are necessary. For convenience, we'll say 3 degrees. 3 degrees pitch down in a helicopter will give you significant acceleration rates. Likewise, if you have a rate and want to stop, 3 degrees pitch up will stop it quite quickly. However, the pilot on the lunar surface is faced with a quite different task. Here is a vehicle with essentially the same inertia as it would have on the Earth is supported by only 1/6 as much lift vector. To get the same rates of acceleration or deceleration, he has to tilt the vehicle instead of the 3 degrees we talked about previously, 18 degrees. 18 degrees pitch up to stop an acceleration or translation, or 18 degrees pitch down look quite different to the pilot from the cockpit standpoint. To give him familiarization with the extreme attitudes required for acceleration and deceleration is the primary reason for learning to fly the lunar landing training vehicle. To expand on these larger pitch angles required in landing the lunar module, here we have a cross-section of the Apollo 15 trajectory. As you can see, at 400 feet, the lunar module is pitched up approximately 17 degrees. This reduces to about 10 degrees pitch at 200 feet, then to essentially 0 at 100 feet, followed by a vertical landing.
The LLTV was built not for beauty, but rather for completion of a specific dynamic training routine. The basic airframe, shaped much like a pyramid, is a tubular aluminum alloy structure. It has a number of structural mounts for systems and equipment. The LLTV has 3 lift engines. A gimbaled turbojet engine with a thrust of 4,200 pounds is the key to simulating a lunar module landing on the moon. Electronically controlled, the engine, during lunar simulation, supports 5/6 of the weight of the LLTV and nullifies aerodynamic forces caused by the atmosphere. Thus, in flight, the vehicle handles as if it weighed only 1/6 as much as it actually does, and as if it were in a near vacuum. In short, as if it were functioning under lunar landing conditions. 2 rocket engines provide the 1/6 G lift vector used for maneuvering during lunar landing simulations. These engines, which can be throttled, fulfill the role of the lunar module descent engine. And the pilot uses them in simulating the lunar landing phase, including translation maneuvers. Clusters of small rockets are used to control the attitude or orientation of the LLTV, the same technique used for controlling the attitude of the lunar module. Both the rocket engines used for lift and translations and the clusters used for attitude control are fueled with hydrogen peroxide, which is pressurized with helium. Much of the electrical and electronic equipment is located on a platform mounted at the rear of the vehicle structure. The landing gear, located at the end of each leg, are basically conventional landing struts. They are designed to absorb both horizontal and vertical shocks at landing. The pilot's cockpit is located on a platform at the front of the vehicle structure. The cockpit is equipped with an ejection seat, unlike the lunar module in which the pilots stand during the landing phase. On one side, flight controls and displays are peculiar to the LLTV. On the other side, controls and displays are near duplicates of those in the lunar module. The hand controller, for instance, is actual flight hardware, adapted for use in the LLTV. The pilot instrument panel also has many of the same displays as the lunar module. Even for men as skilled as astronauts in engineering and piloting, the LLTV is not an easy machine to learn to handle. Before an astronaut ever actually flies a LLTV, he has trained in a helicopter for at least 100 hours. He has trained in an LLTV simulator, completing a detailed program, or syllabus, as the pilots call it. He has trained in a vehicle tethered to a large overhead frame. He has handled the LLTV mounted in a fixture where the vehicle will respond to certain flight commands. And he has powered up the LLTV engines, with the vehicle itself tied down, to become accustomed to the operation of the engines. Only after the considerable training, plus many briefings, is he ready to fly the LLTV. And in the total picture, this is but a small part of the training necessary to learn to fly the lunar module itself.